So today we're going to do some review of sequences and series and exponents. All of these sequence and series formulas are in your formula packet, but it's just good to go through and make sure you understand what we would put in each of the different parts. So like UN, that would give us the value of the nth term, or whatever term we want to find. We've got U1, which is the first term, and that's the term number of the one we want. So if we want the 10th term, it'd be 10. And then D, that's the common difference, or the amount added each time. So common difference, which is the amount added each time. The common difference can be negative when it's decreasing. It's a little weird that D is at the end. Just make sure you're always multiplying, especially if it's negative, because you don't want it to look like we're subtracting D at the end. We do want to multiply D at the end. Really similar for geometric sequences, which are again I forgot to say, arithmetic sequences. That's when we have a pattern that grows by adding or subtracting. And then geometric is by multiplying or dividing. So for a geometric sequence, again, we have our nth term. That will be equal to the first term times the common ratio. And the common ratio is the amount that is multiplied each time. And then a reminder too that even if it looks like division, we can still write division as multiplication. And then like last time, n is our term number. All right, series, that's when we have the sum of sequence, and that's going to be true for both arithmetic and geometric series. Arithmetic, it's the sum of the first n terms, basically. So sum of the first n terms. There are two different formulas. They both will give the exact same answer. It's all just dependent on what you have. So like this one here, you would use, if you know, first and last term. And then if you don't know the first and last term, that's okay, because as long as you have the first term and the common difference, you're good to use this one. I usually like to use this one if I know the first and the last term, just because there's less going on. But if you don't know that, that's totally fine. You can just use this one. So they'll both get you the same answers. Geometric series, we also have two different forms. So again, it's the sum of the first n terms. I guess there should be an S there too. And for that, it's the sum of the first n terms of a geometric series sequence. Pieces all mean the exact same thing. Again, we have two different formulas. These ones are much more similar. Like, they truly take the same information. They just, one of them, the order of subtracting is different each time. Here it's r to the n minus 1. Here it's 1 minus r to the n. So same values, just subtracting in a different order. And the bottom is switched too, which ends up making it exactly the same. So truly either one is good. We'll note that this right here, this isn't really a part of the formula. It's just specifying that r can't equal 1. Because if it could, if we did 1 minus 1, we'd get 0 down here, and we can't have that. So r can't be 1. If it was, if the r value is 1, that would be a pattern that was like 3, 3, 3, because 3 times 1 is 3. 3 times 1 is 3. So the number you're multiplying by is 1. That's not really a pattern you'll encounter anyway. Yeah. Okay, so we'll do a little practice of using these formulas. So here we go with number 1. Consider the finite arithmetic sequence, -3 to 5, and so on. So it's arithmetic, so we know it's adding or subtracting each time. So let's see if we've got, what's the difference between 5 and -3? We've got 8, so our common difference is 8. We're adding 8 each time. We always, never a bad idea to go back and check. Is it true? Is -3 plus 8 indeed 5? And it is, so we're all good there. All right, find the number of terms in the sequence. Okay, so we have a list, so we're gonna want to use our sequence formula here by substituting in all of the stuff that we know or don't know. So our formula, I'll write it down here just so we can see it again. We have the nth term is going to be the first term plus n minus 1 times d. So replacing all the things I know. I know the last term, or the nth term, is going to be 1,189, and then I just need to, oops, that's not the right thing. The first term I know is -3, plus, I don't know n, but I do know that my difference is 8. And now I just need to solve this equation. This unit, we are really going to be practicing a ton of solving by graphing, so that's what I'm going to do here. Yes, we could solve this algebraically, but we also can very much solve it graphically. So I'm going to graph in one line my one half of the equation, and then in another the other half. We will use x instead of n, and that works perfectly good. And then we will graph it. I'm going to use zoom fit just because that often shows us some of it. Okay, it looks like I'm going to have to scroll way out. There's lots and lots of terms in the sequence. These are not close to touching. I'm good in the y values. I don't need to zoom out any there, but I will need to adjust this. So my x max, x max, I'm going to try 100. We'll see where that gets us. Okay, we're closer. Let me go to 200. Doing this, we don't just want to zoom out and out and out. We want to just zoom out the parts that we needed to, and in that case, it was the x's. Now I'm gonna find the intersection by doing second trace intersect, left bound. I'm already to the left of it. Right bound, make sure to get to the right of it. And, oh, okay, usually it says guess, but this is fancier than, I guess, the traditional, but it's going to give us the intersection, so 150, 1189, so it's going to be n equals 1189, and a great way to show your work if you ever solve by graphing is just draw a little sketch of the intersection. So, oh, oops, n isn't 1189. It's 150. Since our x value here is 150 and our y value is 1189. We already knew that one. Okay. Find the sum of the arithmetic series. So we have all of this here. So again, we can use our formula here. So this time we will need to use this one right here, or this one right here. We have the first and the last term, so I'm going to use that simpler one. I guess we have new series too. So we have our formula is sum of the first n terms is the number of terms divided by 2 times the first term plus the last term. So for us, that is going to be, we don't know how many terms, so we're going to have to figure that out first. And then we'll be able to substitute into this formula where we have, so it'll be something, or I'll just leave it as a blank and fill that in a moment. Something over 2 equals u1 negative 10 plus 90. Right. So again, we'll have to find the value of n. So we have 90 equals the first term, negative 10, plus, let's see, how much are we increasing by each time? Plus 4 each time. So plus, where are we? n we don't know, minus 1 times 4. This one I'll solve algebraically just because we just saw it in the calculator. So we've got 90 equals negative 10 plus 4n minus 4. Add 10, add 10. 100 equals 4n minus 4 plus 4 plus 4. Woo. 104 equals 4n, divide by 4, and we've got n equals, what does it equal? 26. So now we can plug that in here, and then I'll evaluate. Let's see, 26 divided by 2 times negative 10 plus 90 equals 1,040. All right. 1,040. Okay, I've got to make that nice and clear since I've got a lot going on in here. All right. One other note I want to point out is if you've got a numerics calculator, there is a whole app that does sequences and series. So this one right here, sequences, we can add a sequence by typing in the equation. So for example, if we have this one here, we could do negative 10 times, or plus, n minus 1 times 4. Times 4. And then I can add it, and that is an explicit, I don't want to add another one. What am I doing? Back. Okay, I promise this can be helpful. Definitely not necessary, we can always use all the other stuff, but we can see a graph. We can also then do things like calculate the sum of the terms. So we can calculate term 0 to, or first term to our 26th term and get the same sum that we just got. So that is also just an option. If you have numerics, I would recommend poking around that up and exploring a bit more. Okay, we'll go back and take a look at this next example. So the third term of a positive geometric sequence is 63, and the fifth term is 567. Find the common ratio and the first term. All right, so I'm going to fill in what we know using some blanks. So I don't know the first term or the second term, but I know the third is 63, and the fifth is 567. It is geometric, so I know it's multiplying. So I know 63 times r again is going to equal 567. So I can set that up as an equation. So 63 times r, or times r squared, since r times r is r squared, equals 567, and now I just need to solve. Again, we could always solve by graphing, but I'll do this one algebraically. So r squared equals, let's see, what do we got? We have 567 divided by 63 equals that. R squared equals 9. Oh, lovely. We can square root each side and know that r is going to be 3 right here. So if r is 3, when we go forward, we're multiplying by 3. So if we go backwards, we're going to divide by 3. So to go this way, we'll divide by 3 once, and then we'll divide by 3 again. So 63 divided by 3 is 21, divided by 3 again equals 7. So U1 equals 7 and R equals 3 are our two pieces. I'm just going to check my work real quick on that one. So is it true? Is 7 times 3 again equal to 63? It is. And then if we multiply times 3 and times 3 again, we get our other given term. So we're all good there. All right, last little piece here, we're just going to review exponential functions a little bit. This isn't in the formula packet, but really it's helpful to know these things, but if you can't, you can usually get away with it just by using your graphing calculator. But the general form for exponential functions is y equals a times b to the x, and then we add on our asymptote that will shift things. So it'll be plus k is the letter we use there. So if our value b here is greater than 1, that means the function is going to be increasing. And we have exponential growth. If b is between 0 and 1, that means we're multiplying by a fraction, less than 1 or decimal. That's going to be decreasing, since multiplying by numbers like that make numbers smaller, so we have exponential decay. The y-intercept would be when you were just in Algebra 1, you saw exponential functions that were like this right here. This is where we ended, and a was the y-intercept in those cases. When we have this value of k, we need to add that to a. So these two together form our y-intercept. So it'll be y equals a plus k. Not a huge deal generally if you don't remember that, because we can just graph it and find the y-intercept. Similarly, if you can't remember what part is the asymptote, which is this part right here, is the asymptote, then you can graph it and find it. So that asymptote will be at the value y equals k, because it's going to be a horizontal line at the value of k, high from it. All right, we're going to look at these ones in a graphing calculator too. So find the initial length of the ivy plant. So this one, that's basically asking what is the y-intercept, and our y-intercept is a plus k. We don't have a value for k. It's just 2, because that's our y-intercept when we don't have a vertical or horizontal asymptote. So 2 meters. If you remember, again, I just love Algebra 1. So if you can recall it back with me again here. Oops, I thought that would disappear. The kind of 2 questions we're asking yourselves a lot with exponential functions is where does it start, how does it change? So that where does it start is 2. We just have to sometimes adjust now that we have a horizontal asymptote. All right, find the length of the plant after 10 weeks. We can, since x is the time in weeks, we can just replace x with 10. So f of 10 equals 2 times 1.1 to the 10th. So let's see, 2 times 1.1 to the 10th power is 5.19 meters when we're rounding to 3 sig figs. So 5.19 meters. All right, find how long it takes the plant to reach a length of 10 meters. Here is where we would set up our equation. Now we know the length, we don't know the time, so we're going to replace our output f of x. So if 10 equals 2 times 1.1 to the x, and then we will solve this. I recommend solving this in your graphing calculator again, so just going on back there, we graph one side of our equation and the other side. Oh, not that. How about to the power of x? And then find our intersection. So there we go. And we've got the intersection being, it'll be x equals 16.9, and that would be weeks. If you solve in a graphing calculator, the way you show your work is by setting up this equation and or graphing. I'd do both just to make sure you can always get any of those marks. So 16.9 comma 10. If we wanted to solve this algebraically, we would need to use logs. If that sounds scary, go ahead, solve by graphing. In SL at least, that will always get you where you need to go. There could be sometimes in HL that you would need it if you're headed there. But if you did want to solve for logs, with logs, it'd be 10 equals 2 times 1.1 to the x. We would divide by 2, get 5 equals 1.1 to the x, and then we do log base 1.1 to the 5 equals x, and then we'd solve that. If you're in NumWorks, the place you find log is this toolbox here. So you click this button here, you'd go down to log base 1.1 of 5. We'll see that we get the same thing. And then a reminder in TI, you would find that you'd hit math and then scroll to log base. And then it lets you put it in. So again, 1.1 and 5, and there we go. Okay, something you will see, I think, when we do the funky functions packet in class, you'll definitely see E somewhere. E is an irrational number, kind of like pi. It has a value that goes on forever, 2.71828. It's called the natural number because it happens to show up in lots of areas of math naturally. And all you really need to know about it is it's just a number and we can access it in our calculator. So if you ever have a function where you're trying to figure out, or I'll use function notation, if you're told like, oh, f of x equals 4e to the x, and you're trying to figure out what is f of 3, you would just, like we normally do, replace x with 3 and then use your calculator. So we have a button for E. In a TI, it's with this button, ln. You have to hit second ln, and then you can just treat it like a number and type it all in. So it'd be 4 times second ln, I get the E to the third power, and I'd get my value. So f of 3 equals 80.3. So E is just a number. Once you know about E, you'll probably notice that E is very rarely used as a variable in math, and the reason why is because it actually stands for a very specific number here. So E is just a number. Use the calculator button. So use calc button, which for a TI is going to be second ln. On NumWorks, it is slightly different. I think the button is E directly. Yeah, so we just get E to the x down there. So up here. Yeah. All right, that is all we got for today. So, yeah, see y'all next time. Or in class. Okay.